So we are attempting to figure out if we have a sphere and we know that there is a cylinder that can barely squeeze inside said sphere. We wish to find out which of the cylinders that could fit inside this thing has the most volume and the most surface area. Now I'm going to be assuming that the radius of the sphere is 10. If I think about this logically, there is a super flat sphere that reaches all the way across this equator, essentially. It will have a large top and a large bottom, but it has no walls on the side. It also has zero volume. Likewise, I could assume a very skinny sphere, one that's exactly 1 point wide in the middle of this thing. That stick would have a lot of lateral surface area, but no bases and also no volume. So somewhere between those two extremes is going to be a cylinder that has the best of both worlds. And our goal is to try to figure out which of these cylinders is it going to be. So first thing I want to do is remind myself what are the formulas for the volume and surface area of a cylinder. My volume formula is the base times the height. My surface area formula is 2 bases plus the circumference times the height for the lateral surface area. I'm going to split this down and try to think about these two concepts independently of each other. Now, when I'm dealing with 3-dimensional figures, I like trying to redraw them in 2 dimensions to see if any new insights come out to me. So from the side, my cylinder all of a sudden looks like a rectangle, which isn't terribly interesting, but I notice a few interesting things here. First, I don't know which cylinder is going to be the best one, but I know it's going to have some kind of a radius. I'm going to call this radius term x. We're trying to solve for what radius of a cylinder will result in having these traits that we're looking for. I also notice that if this distance is x, this distance is going to be the original radius of my sphere, which is 10. By definition, the corner of the cylinder is touching the edge of the sphere, so it must be 10 units away from the center. I also have this term here, which is going to be my height of my cylinder divided by 2. But cylinders contain that right angle there. Every layer of the cylinder is at a right angle to its walls. This means that I can write a little Pythagorean theorem expression here. The radius of my cylinder plus the height of my cylinder over 2 squared has to equal 10 squared. Put another way, x squared plus 1/4 h squared equals 100. This means that 1/4 h squared equals 100 minus x squared. This means that h squared equals 25 minus 1/4 x squared, or that the height of my cylinder is the square root of 25 minus 1/4 x squared. What I now have is an expression for the height of my cylinder that only uses x. So if I'm writing the volume of my cylinder, which is pi r squared times height, that means the volume is pi times my radius of my cylinder, which is x squared, times the height of my cylinder, i.e. the square root of 25 minus 1/4 x squared. Likewise for surface area. It equals 2 pi times the radius of my cylinder squared plus 2 pi times the radius of my cylinder times this ugly gobbledygook of 25 minus 1/4 x squared. Now these two expressions look really disgusting. But you know what's really good at handling disgusting expressions? Calculators. We can totally throw these expressions into our calculator and let it graph all of the possible spheres, or all the possible cylinders that could fit inside a sphere, and tell us what their volumes are. All we then have to do is find which one has the maximum of them. Their graphs are going to have some kind of a peak in between places where there is 0 volume, when our radius is 0, and when there is 0 volume when the radius is 10. Somewhere in the middle is where our peak is. And all we have to do is throw that into our calculator and ask it to find out where is the maximum value to get our final answer.